Today, I make a presentation titled Tactile-based curiosity maximizes tactile-rich object-oriented actions even without any extrinsic rewards. Tactile information is critical for human object manipulation, but how can the dexterous object manipulation be acquired? We would like to consider it with human development from perspective of curiosity. Infant approach to object curiously. Infant behaviors look as if they explore their body and environment. They curiously approach an object and try discovering a new tactile responses. They perform actions as if they confirm tactile responses during exploration. From developmental point of view, the behaviors tend to change as they grow from random movement to intentional movement. According to developmental psychology, they are attracted to novel tactile responses such as texture rather than familiar tactile responses. So we began to consider curiosity based on tactile sensation. Recently, artificial curiosity models in reinforcement learning are proposed. Such methods are beneficial for efficient exploration in an environment with sparse rewards. The curiosity is defined as an internal lever to lead to novel status. One of the methods of artificial curiosity is self-supervised exploration via disagreement by Deepak. The internal levers of the method is defined by variance of multiple prediction network with random initial weight. Through the training process, only internal levers with visual information induce picking action in exploration. We think that this kind of method can be used to model human developmental behavior acquisition without any special external purpose. We hypothesize a scenario for object manipulation acquisition in human development. First of all, random actions by an infant and intentionally approach object. Tactile-based curiosity tries to make sure tactile responses repeatedly. Infants get tired of actions where tactile responses are easily predicted. The internal levers leads increase of actions that are difficult to predict tactile response. As a result, dexterous object manipulation emerges. Based on this scenario, we investigate this hypothesis until the fourth step by constructive approach. Approach of this research is observation of analysis of behaviors of agent simulation with tactile-based curiosity models. The simulation is a two-dimensional physics simulation in the environment with a robotic agent and a movable object. To validate the effect of vision and tactile modalities, we compare different modality patterns. After the experiment, we observe agent behaviors qualitatively and analyze touch frequencies for the object. The simulation consists of the mobile agent and the object. The agent can move orbital positions and rotate the arm with the end effector. We prepare visual information and tactile information for their curiosity. We compare the tactile-based curiosity with for patterns of sensation from the end effector, arm, church, and whole body. This is the schematic of the disagreement model for curiosity. The point of the model is the reward. The reward is defined by the variance of the predictions of multiple prediction networks. The prediction network receives same input. The training of the prediction networks starts with different initial weight. So the expectations of the predictions by the networks are gradually same for frequently experienced input. By the model, the prediction target is a regarded curious target. In our experiment, the input is visual information and action. We change the output to compare different curious sensations. Robotic actions consist of step 1 and step 2. Step 1 is the church's movement to the next position. After the movement finished on the position, then the agent rotates the arm to the angle theta. The position and angle are discretized, so the action space has 3,200 actions in total. The observed image is the whole area inside frame with 400 times 300 pixels from top view. The visual feature is calculated by random CNN. The feature is a vector with 412 dimensions. Tactile response is two-dimensional. If the agent touches the object by a body part during the action, the tactile response is 0, 1. Otherwise, the response is 1, 0. We conduct the 6 modality conditions. To observe the effect of tactile-based curiosity, we conduct a control experiment only with vision-based curiosity. To compare the condition among tactile-based curiosities, we prepare 4 curiosity conditions to the end effector, the arm, the chassis, and the whole body. This is the results of vision-based curiosity and visual tactile-based curiosity. You can see that the vision-based curiosity does not induce noticeable interaction to the object, while visual tactile-based curiosity induces interaction to the object. Change of self-image stimulates the vision-based curiosity, then dancing-like movement appears. This is the results of tactile-based curiosities. You can see that each agent hits the object by the respective body part that is target of curiosity, as if the sensations lead the behaviors respectively. We do not show the analysis because of the time frame of the presentation. Please see our paper. Conclusion. We investigate the hypothesis that curiosity through tactile sensation induces the emergence of tactile-rich object-oriented behaviors. The experimental results indicated that the hypothesis would be correct. The study is preliminary because the experiment is only conducted using very simple computer simulation. Now we are planning and conducting experiments with more complex systems. For example, now we are conducting this type of simulations with other type of robot and object. Do you think that the behaviors look to be induced depending on the curiosity target? Thank you for your kind attention.